Hello! Welcome to our video on gases. A gas is one of the three states of matter. It is a substance that has no fixed shape or volume and which will expand to fill the container that houses it. Gas molecules can briefly collide with each other, but seldomly have real interactions. Gas molecules' conditions are dependent on the pressure, volume, temperature, and amount of such gas. These variables can describe the behavior of gases using a series of gas laws. Let's talk about those laws. In 1661, Robert Boyle established that a given gas's volume was inversely proportional to its pressure at a constant temperature, meaning that when the volume of the gas increases, the pressure decreases, and vice versa. This law can be used to predict what happens if there is a change in temperature or volume of a given gas. For it to work, the number of molecules and temperature must remain constant. The formula, initial pressure times initial volume equals final pressure times final volume, describes such relationship and is used to determine the value of the unknown variable after a change in pressure or volume has occurred. Like Boyle, Jacques Charles studied the behavior of gases, but did so while maintaining a constant pressure. He observed that when the pressure of a given gas remained constant, the volume of the gas increased if the temperature increased. A rise in temperature increases the kinetic energy or movement of the gas particles, therefore pushing the walls of the container that houses them. The formula initial volume divided by initial temperature equals final volume divided by final temperature can be used to determine the unknown value following a change in one of these variables. It should be noted that for this law to work, both the amount of gas and the pressure must remain constant. But what happens when the container that houses the gas is not flexible and therefore the volume cannot be increased when the temperature increases? This is where Gay-Lussac's law comes in place. It is basically the same principle as Charles' law, but here the container is rigid versus flexible. Since the container cannot expand for the volume to increase, then the volume has to remain constant. And what happens is that with an increase in temperature, the rapidly moving gas particles try to push against the rigid walls with force, therefore increasing the pressure inside the container. In summary, if the volume remains constant, a rise in temperature will lead to a rise in pressure. So far, the three laws discussed maintain one variable constant. Either the pressure, the temperature, or the volume has to remain unchanged for those laws to work. So how do we predict the behavior of a gas when all of those are allowed to change? We use the combined gas law. This law does just that. It combines Boyle's, Charles', and Gay-Lussac's individual laws into one. When this is done, one can solve for any of the variables and establish the behavior of the gas. The mathematical formula that allows for this to be calculated is expressed as initial pressure times the initial volume divided by the initial temperature equals the final pressure times the final volume divided by the final temperature. If we want to account for the amount of gas molecules in a container, then we use Avogadro's law. This law states that the volume and number of molecules are proportional at constant pressure and temperature. We can use the formula initial amount in moles divided by initial volume equals final amount in moles divided by final volume and solve for the variable in question. When we add Avogadro's law to the combined gas law, we can derive the ideal gas law. An ideal gas is a hypothetical gas that is presumed to mimic the behavior of most gases under most conditions. The ideal gas law assumes that both the volume of the gas and forces between the gas molecules are small and have no effect on the overall behavior of the gas, and it uses a constant R. What is R? R is the proportionality constant. If you recall the previous gas laws, you'll know that for all of them, one constant is either proportional or inversely proportional to another. The ideal gas law replaces that proportionality with a constant known as R and with a value of 8.3145 liters times kilopascals divided by kelvins times moles. Using the ideal gas law, if one knows any three things about a gas, the fourth one can be deduced. One thing though, all gases deviate from this law at low temperatures and high pressures. In summary, gases are a state of matter. Gas molecules rarely interact with each other. Gas properties can be described using a series of gas laws, and the ideal gas equation can be used to predict the behavior of a real gas. In this video, we have gone over some of the properties of gases. For more videos like this, visit our YouTube page titled Ask ASC. Thank you, and have a great day.